Hey there, folks. I'm Nick Cutsup, a graduate student at Cornell. Today, I'll be talking about the distribution and properties of haze in Pluto's atmosphere determined using observations from New Horizons. This work was recently accepted into the Planetary Science Journal, and it's available right now in preprint on arXiv. So, over the next couple of minutes, I'm going to try to convince you of these conclusions here. First off, Pluto's atmosphere is distributed roughly into three regions of aerosol growth. The upper atmosphere, where photolysis is still going on, there's a single population of small-sized scatterers. Then, from 200 to 60 kilometers, where photolysis has ceased, we experience rapid aerosol growth, and we have an abundance of small and large-sized particles distributed roughly into either a power law or a bimodal-esque distribution. Then, from 60 kilometers down to the surface, we have the same distribution of particle sizes as before, but now as the temperature drops and we're interacting with the planetary boundary layer, our aerosols experience little growth. In order to accomplish all of this, the aerosols must form through fractal aggregation. They have to have a fractal dimension less than 2, and they need to have a charge to radius ratio of at least 60 electrons per micron. On July 14th, 2015, New Horizons flew by Pluto and acquired the first high-resolution images of the Pluto system at a variety of wavelengths and over the full range of phase angles. Here, we are using observations from the MVIC, the Multispectral Visible and Imaging Camera, in the red, blue, and near IR filters to construct phase curves of Pluto's atmosphere using the limb scatter technique. But before we could do any of that, we needed to remove an off-disk glow caused by stray light or some other spurious brightness in the instrument. We know that this off-disk glow is not entirely due to the haze in Pluto's atmosphere because the same glow is visible around Charon, which is an airless body. So, in order to remove this spurious brightness, we use Charon as a model and subtract that part of the signal off to get our final data set. So now we're able to make our phase curves, and with the limb scatter technique, we're able to do this at discrete altitudes. The full radiative transfer equation that accompanies the limb scatter technique includes first, second, and nth order scattering events. However, due to Pluto's optically thin atmosphere, we can ignore everything except the single scattering event from just the haze. We can also ignore Rayleigh scattering from nitrogen and methane in Pluto's atmosphere, as this is many orders of magnitude lower than the single scattering from the haze. So now we have the scattering phase curve for Pluto's haze, in this case from 20 to 40 kilometers, and what you'll notice immediately is the steep high phase component to Pluto's haze. What you'll also notice is the not insignificant amount of low phase scattering that we have. This is interesting because Mie scattering is identifiable by a steep forward scattering component and an almost zero back scattering component, while Rayleigh scattering is identifiable by isotropic scattering. The problem is Mie scattering occurs with particle sizes about the same size as the wavelength of light, whereas Rayleigh scattering occurs when the particle size is much less than the wavelength of light. So in order to have both of these aspects in our phase curves, we need to have a distribution of particle sizes. So we modeled scattering phase curves caused by a distribution of particle sizes and compared them to our observed phase curves. We modeled monodispersed, power law, bimodal, and trimodal distributions. We also compared these distributions to the results from Gao et al. 2017, which used a log normal distribution. Below 200 kilometers, we find that a power law, bimodal, or trimodal are able to fit our phase curves reasonably well. The log normal distribution from Gao is unable to match the duplicitous nature of our phase curves due to a paucity of Rayleigh-sized scatterers around 10 nanometers and MVIC-sized scatterers around 700 nanometers. So now we can start talking about how the population distributions change as a function of altitude. Over here on the right, you can see the amount of forward scattering and back scattering in all three wavelengths as a function of altitude. As before, you can see below 200 kilometers, the phase curves are highly forward scattering with a not insignificant amount of back scattering, but above 200 kilometers, the scattering is nearly isotropic. This jives with our modeling, as we found that above 200 kilometers, it really didn't matter what population type we used. Everything approximated to a monodispersed population, suggesting that this region is composed of a single particle size in the Rayleigh scattering regime for all three wavelengths. Below 60 kilometers, you'll notice that the slope of the high phase component has changed, indicating that the rate of growth has decreased for this area. So in the upper atmosphere, we have an abundance of small-sized scatterers. This is similar to the results from GAU 2017. In order to maintain our backscatter component, however, the small-sized scatterers cannot be removed from the atmosphere by destruction or combining into larger particles. We also find that the maximum particle size needs to be about 1 micron in order for the phase curves to match the slope of the forward scattered component, while not contributing too much or too little to the backscatter component. In order to accomplish this, the growth rate must be slow enough that small-sized aerosols are produced faster than they can be combined to form larger particles. However, all of the aerosols must spend enough time in the atmosphere such that the very large 1 micron particles can be formed. The slow growth rate is due to a high charge to radius ratio, larger than 60 electrons per micron, while the long lifetime in the atmosphere is due to the aerosols having a fractal dimension less than 2, which decreases their sedimentation velocity. This all then produces the particle size distribution map you can see on the right. And that's the end of my talk. Thank you very much for tuning in, and keep an eye out for this paper in an upcoming issue of the Planetary Science Journal.